from Tianjin University, and Professor Hua Zhang from City University of Hong Kong. Today, Professor Anthony Fajty from Northwestern University will give us a presentation. Professor Anthony Fajty is a co-founder and currently the Chief Technology Officer of Flex Terra Corporation. He is also an adjunct professor at the Northwestern University. He has published more than 450 research articles and 15 book chapters and holds more than 120 patents. He received the ACS Award for Creative Invention, the Giulio Natta Gold Medal of the Italian Chemical Society, the Team ID Texas Printed Electronics Europe Award, the Corporate Flex Tech Award. He is a fellow of National Academy of Inventor, MRS, AAAS, PMSE, Kavli, and RS Fellow. He was selected among the top 100 material scientists of the past decades and recognized a highly cited scientist by Thomas Reuters. Today, Professor Anthony will give us a presentation about the unconventional materials and the transistor architectures for coupled ionic-electronic charge transport. Now,
I'm going to talk a little bit about very briefly about material and new transistor architecture to enable coupled ionic and electronic charge transport mostly. So for the outline, I'm going to start with a very, very brief introduction, very briefly about an example of molecular design for OTFT. This is a little less hot topic at the moment, but there's still new chemistry we can do. And then quickly, I want to try to talk about three areas. One about enable stretchable OECT using morphologies as a key element. A new example of a device architecture for OECT type of devices. Then a couple using electrolyte as a key element to make complementary circuits. What we have been interested in now for several years has been to develop electronic material for different transistor architectures, going from FT architecture, where the key element is the gate dielectric, which is polarized. So you have charge transport which happens in the semiconductor only at the interface between the dielectric and the semiconductor, or using electrolyte as a polarizing dielectric. And here, the semiconductor is impermeable to ions, or the ions cannot penetrate, to have an ion motion here, and the charge carrier remains interfacial. Or in OECT, the semiconductor is permeable to ions, so the ion can penetrate into the semiconductor. And you have a bulk charge transport, which is associated to a redox chemistry of the semiconductor. So these are all transistor architecture, but with somehow very different function. And what is very different is the charge transport. Usually TFT is better when you want to operate the device at high frequency, for example, for display. And instead electrical double layer TFT or OECT, the operating voltage is much lower, particularly for OECT. This is, and for OECT, you can have very high currents or very high transconductance. Low frequency, but much higher switching currents. In the area of TFT, so this type of device, we have done a lot of work in designing material N-type shown here. These are examples of type semiconductor. And we have learned really a lot in the past 20 years. There is we know how to position orbitals, how we design material, what kind of substituents to use. But there are still some interesting things we can do. For example, this is a good N-type polymer, but it's unusual. This is a twisted backbone. So you usually want to have a planar backbone. So what we have done here is to remove progressively one carbonyl group from 4 to 3 to 1. And If you do this, these are a molecular structure from 4 carbonyl, 3 carbonyl, 2 carbonyls. These are crystal structure. These are not computation. And you see here that the average torsional angle is decreasing, particularly for the very last molecule, for the very last unit. And when you have this type of unit combined with a proper monomer, we can actually achieve quite high electron mobility, much larger than the standard 2200. There is chemistry you can do to do that. Other things we have done is, excuse me, to design type again. And one element to create type is to have these building blocks which have what are called intramolecular lock, so interaction between sulfur and oxygen prevalently, sulfur-sulfur, or sulfur-fluorine. So we ask ourselves, can we actually use selenium as an element to analyze the core? And the question is going to be planar. This is the first question. Also, for those of you who are familiar with OTFT, you know that selenophene is a very good building block to make TFT material. Usually, selenophene-based material building blocks show higher mobility than the sulfur, than the thiophene, which have higher mobility than the oxygen. The question is, what happened here in this series? Selenophene polymer or molecule which have a higher mobility than the sulfur and the oxygen. So there's two questions: planarity and about mobility. To answer this question, we made a lot of molecules. I want you only to look at these three with the selenium, the core, the sulfur, the oxygen. Okay? The first question is about planarity. So we made the crystal structure of all the three molecules. And what you see here, also in the case of selenium, this is the core is completely planar. The intramolecular lock angle, the intermolecular torsion is 0, so identical to the one of the sulfur molecule, 0, identical to that of the oxygen molecule, which is also 0. So selenium there, but you still have very strong intramolecular lock. So the molecules are planar. And then we made devices. I'm going to try to go into the detail. I just want to look at the compounds here with the selenium. This is the field effect mobility. And you see here that when you use selenium, the mobility is an average, or the maximum mobility is larger than the sulfur, is much larger than the oxygen. So selenium is also very effective to enhance the charge transport, and you do not have to incorporate it as a selenophene. You can also use a selenoalkyl chain to enhance the charge transport. Now let me switch about stretchable and flexible devices. And as organic chemistry, we think that organic semiconductors are soft, so they are plastic or plastic. But this is typically not the case. This is typically not true in many cases. For example, we have these two polymers we made a few years ago, that are N-type polymer, and we can make a film on elastomers and stretch them. If you look at this video here, hopefully it's going to start. Yes, see this black area here, you're stretching in this direction, and you see formation of crack. The crack form for both polymer is quite low strain, only 3-4%. This is the Young modulus. If you compare the Young modulus of this polymer versus conventional material, these are much lower. Okay, it's good. If you compare to real elastomers, these numbers are very, very large. Okay, these numbers are very large. So you want to lower the Young modulus, and the opposite is for the crack onset. This is very low compared to real elastomers. So the question is, can we make this material more elastic, more plastic, hopefully, or elastic? And what is interesting is we can take the same polymer. Instead to have the polymer on an elastomer, we embed the polymer between two elastomers. So this is exactly the same polymer, N2200, but here is only on EMS, and here is covered with polyurethane. When you do that, you can stretch the same film 50%, there is no crack. Instead, if there is no, the polymer is not embedded, the crack occurs about much lower, about 3%. So you can do things like this, or you can also do chemistry. And this is an example where we have actually mixed a conjugated unit with a conjugated unit. When you do this, the polymer becomes much more soft. So we can do chemistry that helps to soften the polymer. But the question we ask is, can we actually do the same thing that people have done for metals? So if you take a metal line and you stretch it, it cracks, right? But if you have a serpentine or gold metal, or you have this resin feature, you stretch them, they don't crack because there is a morphological plastic embedding into the film. So can we do this with organic? This is the question. And the other question is without photolithography, because organic are very difficult to do photolithography on top of them. All these structures were made using photolithography. So one way we have been able to embed porosity, this is not like this, but it's very similar to a certain extent. These are AFM of 3 materials, organic, where we have fabricated by breadth figure. The figure is a technique where you can spin coat polymer or a molecule solution. You have your semiconductor plus a little bit of polystyrene to spin in a very high relative humidity atmosphere. Water condenses on the film before the solvent completely evaporates. So water droplets creates holes to your film. What you see here, the black area where the water was present, and around it, the lighter area where the semiconductor plus a little bit of polystyrene is present. This is a very easy way to have holes into your film, into semiconductor film, without using photolithography. So it's a sort of photolithography done very, very easily. We can use this semiconductor porous semiconductor film to make, for example, TFT, where because the analyte can penetrate much better, we can have more sensor TFT. We can make these electrochemical transistors. Recall, electrochemical transistor, the ion has to penetrate. And because you have holes, the ion can penetrate, so you can have a higher current compared to the dense film, the film without porosity. These are the people that did the work, very great student and postdoc and visiting scholar. So we showed that, we demonstrated that. We did also another step, which is we actually make holes without any polystyrene, because polystyrene is not an active material. And you see here that are 3 polymers. Again, using breadth figure, we can find conditions to create these holes into the semiconductor. And also another question is, can this porosity always useful for OECT? The answer is yes. These are the currents for different devices. Black is the conductance, the transconductance for the dense film in red here down. And the blue is for the porous. And you see here that no matter if you are using different polymers, these are different polymers or different electrolyte, in all cases, the blue is on top of the black, of the red. So it means porosity is also very good to enhance ion penetration and enhance the current in these devices. However, the question remains, can we actually do better? These are not really good morphology without polystyrene. You see, they are not really very nice interconnected network. It's just greater than really porosity. And this is something we have done more recently. This is an SEM image of a semiconductor, this polymer, without any polystyrene, in breadth figure. And how did we achieve this very nice honeycomb morphology? By using an amphiphilic polymer, which has both an hydrophobic, this is here an alkyl, and a hydrophilic chain, so you need to have both. The other variation is when we prepare the film, we don't spin coat on glass or silicon oxide, but we spin coat on top of a film which has a little bit of polyvinyl alcohol. Polyvinyl alcohol is very hydrophilic, so water really likes to condense on the substrates, and it really helps to create this very nice morphology. So this polymer, we made dense film, we made this whole honeycomb film, and then we made the device on glass. And the device on glass has been fabricated by, we made the film on PVA, and then we put the film on water, PVA dissolves, so the honeycomb or the dense film floats in water. Then we transfer them on the OECT platform, on the contacts. And you see here that when we compare the OECT performance for the dense and the honeycomb film, the porous film, see here that the hysteresis is reduced and the current is higher. Here you have 12, you have 8. So also for this polymer, porosity works better in terms of charge transport. But the key question is about mechanical properties. So, so the question is, are the porous film more elastic compared to the dense film? So we made this film dense or porous on elastomer, and then we start stretching them. Here we stretch it in this direction. You see here that for the dense film, about 60% you form crack. And instead for the honeycomb film, first crack starts on the order of 100 and 120. So indeed, having this honeycomb structure helps the mechanical deformation. And we did also computation this by finite element analysis. And the reason why the honeycomb film are more stretchable is because you have out of plane deformation of the structure. They basically, that remain flat, it goes up a little bit when you stretch. And going up, it helps to dissipate the mechanical energy. Then we started making devices and started to understand the charge transport when you stretch the film. But we wanted to study the stretching independently of the contact deformation, okay? And in order to do that, what we did, we have fabricated the dense or honeycomb film on a substrate, then we stretch them at different degree, okay? Then we laminated the stretch film at different, the stretch semiconductor at different extent on top of the contact, okay? Then we finish the device. In this way, you have device where you have stretched the film at different degree, but the WL remains the same. So there is no variation in the quality of the contact. This is very important to study the charge transport independently of the stretch. And when you do this, these are examples of the device dense film stretched at 60% and then laminated. And this is the second one here, the honeycomb film stretched at 90% and then laminated. What you see here, this is the transconductance current when you stretch. And what you see here that for both, this is the dense film, this is the honeycomb film. In all cases, the transconductance decreases, and this makes sense. That makes completely sense. The reason is because I stretch the film, and then I put it between the source and drain, which are exactly the same. So you stretch, you have less mass, you have less ions, so the
Why, Antonio, why your mic was switched off?
you hear now?
Yeah, it's okay now.
Yeah, I hear you. I make a mistake. Sorry.
So strange. I was in the same position. Sorry, so let me 1 second go back to the highlight. And no, I need to go to. Okay, I can use the yellow. That's okay. So did you hear about the transconductance decreasing or not?
I can hear you.
Okay.
It's clear.
Yes,
So,
yes.
so here the current is decreasing for the dense film, also for the honeycomb film. And this makes completely sense. The reason is because we have the same WL, but we stretch the film, the semiconductor, so there is less mass between the source and drain. Less mass, OECT is bulk charge transport, so you have less current. So the current must decrease when you stretch. But if you normalize the current, the transconductance with the strain, it means you normalize for the mass of the material in the channel. Then you see here that as it decreases a little bit, then it decreases a lot when you're about 60% because she starts cracking the film. Instead, the honeycomb remains stable up to about 100%. Then 120, they start cracking. And the reason is because if you go back here, 120 when it starts cracking. Okay. So this is class that increase the H film are the charge transport in the honeycomb film are insensitive to the charge to the stretching when the WL remains stable. But this is not useful in real devices, right? In real devices, you stretch the whole device. You don't stretch just the semiconductor and you laminate it. So you want to have a stable current when you stretch the device. So you would like to have this current to remain stable, not normalized current. So in order to do that, what we did is we used the honeycomb film, a pre-stretch substrate. So basically what we do, we take an elastomer, we stretch it, we put the source and drain, we put the semiconductor, and then we release it. So everything goes compressed. Then we finish the device, and then we start stretching. Let me explain this a little better. So basically what we did, we take a substrate, we stretch it. For example, here is stretch 100%, you double the area of the substrate. Then you laminate the honeycomb film on top here. And then you release everything French, right? Because the substrate is released, the PDMS is, or the SEBS is elastomer, it goes back, everything gets crunched. And these are how the morphology of the film look like here, in this position, before. And then we start stretching this pre-stretch film and we release it. We stretch at 60% and go back to 0, 100%, 120, 140. You see here that if you look at this SEM, they're identical. It tells you that there is no morphology variation. So the honeycomb film on top of the pre-stretched substrate is elastic. There is no variation in the morphology. So no variation in the morphology. If you do the same thing with the dense film, you start stretching. You see that here, after stretching, this morphology changes. So the dense film does not crack, but the morphology change. It tells you that the dense film on a pre-stretched substrate is a plastic film, but is not an elastic film. So in order to get an elastic platform, you need to have a honeycomb film. This is the message. This is very important. And when you do that, only if you do that, current does not change with the strain. Okay? This is not normalized current. This is DM. It's not change because the combination of the honeycomb plus the pre-stretch. And we did all the experiment about stability and things like that. This is not important. If you're interested, you can look at the paper. But really the key message is the combination of the pre-stretch and the honeycomb. If you do the same thing with the dense film, you will see a variation of the current because the film is plastic. We made a number of devices because the current is stable. Now let me talk a little bit about another thing about OECT. You know, there's a lot of interest in developing OECT, and interesting in terms of material. There's still the challenge about the N type being lower than P type. This is typical. is a limiting cycling stability. There are very, very few examples of CMOS, and this is to do that you have to really use WL, which between the P and the N, OECT, very, very different. So there is challenging in device fabrication because you must use photolithography. OTFT, you can have micron, 50 micron, 30 micron, you can use shadow mask. But OECT, the distance between the source and drain is on the order of 1 micron, 2 microns. So you cannot do it by thermal evaporation through a mask. So it remains challenging. So can we make devices which are easier to make, first question, and can we get good CMOS performance? And the way we did it is to go from a conventional OECT architecture, which is planar. So here you use photolithography, and this distance is a micron, to a vertical architecture, where basically you deposit the first gold line, the semiconductor. It doesn't have to be patterned, as a matter of fact. Then you deposit cross bar a second gold line, and this distance is the thickness of the semiconductor. Basically, this distance here is the distance between the semiconductor in this vertical architecture. Obviously, the obvious question is, if you put two electrodes on top of each other, the ion has to penetrate here. So the question is, can ion be injected? This is what it is challenging in a vertical OECT. Also in an OTFT architecture, vertical architecture has been made, but you need to use a porous electrode. There is some example of pseudo VOECT, but not really truly OECT. For example, if you look at this architecture, this is called a vertical architecture, but in reality, the charge transport is planar. It's just a vertical contacts, but the transport is completely a planar transport. This is true for many other devices because the challenge is to get the ion to be penetrated into the contacts. And we have been actually we have been able to make this device which function quite well. We use two polymer. This is an example of a type, which we call this G2T. And this is a ZN type, which is an homo DT. The way we did it is blending this semiconductor with a little bit of this insulating polymer, which is a cellulotic polymer, which is very hydrophilic. And this is the cross-section of the device. This is the channel. And these are the gold and the gold. So what is at the top and the bottom. And this is in between is the semiconductor. This is the top view of the semiconductor. First, I want to really acknowledge Wei Wang. He's the one who invented the structure. He did most of the work. He's the one, he did really a lot of his work. I have to acknowledge him. Excuse me. So we can make this vertical OECT, and how they work. Actually, this VOECT, they work really beautifully. These are the device type. See here how this current saturates really nicely. How this is the N type. Type achieve the same current level than the P type. Completely different behavior than the conventional device, the planar device, where the P type is much better than the same N type. Also, the question is, are you confining the ion only at the interface, or the ion are really penetrating through the bulk? And in order to demonstrate this is a completely bulk process, these are different couple of VOECT with different areas, okay? But they have the same interface. Sorry, actually my printer doesn't show well. The interface is the same in all devices. The area changes. You have only interfacial charge transport, you should get the same current in all devices. But what we see here that the current increases linearly with the area. So it means it is a completely bulk transport. The ion really penetrates, although the interface is only 100 nanometer thick. I don't know if this, you can look at the video here. I don't know if it's gonna work. Yes, you see, probably went so fast that there is a lot, you see the front of the ion penetrating through the two electrodes when the voltage is swept. We also studied the transient time for these devices. They are in the microseconds, so the devices are very, very fast. And also, what is very, very interesting in this architecture, we can actually put a P-type and N-type OECT, one on top of the other. So we can make these vertical circuits, vertical complementary circuits using vertical transistor OECT. And they really perform really nicely with a very nice gain, very, very large for OECT. And we made also a different circuit, ring oscillator and other things, but this is not so important. Okay, the last 5 minutes, I think I actually went a little bit too fast, but we have time for discussion. I showed you an example where we use OECT as an electrochemical transistor where the ion penetrates. There is another device which is called an electrical double layer TFT, where here instead the ion do not penetrate because the semiconductor is impermeable. And we wanted to make a complementary circuit using electrolyte as the gate electric. But when we started this work, you know that the organic are the best for type, and the metal oxide are the best for N-type. And this type of material, they actually are perfectly suited for organic, for a OECT, because the ion can penetrate, and metal oxide, which are impermeable, and are N-type, are best suited for an electrical double layer. The question we ask ourselves, can we combine OECT organic with an electrical double layer TFT organic to make complementary electrolyte gated complementary circuits? So the idea is to make something which looks like this. But to do that, we have first to pick the P type, and based on this porosity, we use this polymer. It's slightly different to the one I showed you before, but very, very similar. This I showed you before, this works very well as an OECT. A nice current, quite low hysteresis. I want you to remember this number, about 2 to the 5 minus 0.06 volts. We want to find a N-type which matches these numbers. And we use as an N-type IGZO. We tune the indium-gallium-zinc ratio such a way to get a composition which is this one, 1:1:1, where the currents, the on-off ratio, and the on are similar to that of the P-type. When we do this, we can match the TFT, the transistor performance. Then we have to build the inverter in this particular state, or the circuits. And the way we did it is by using photolithography. We first define the IGZO. Again, using photolithography and gold and chromium, we finish the first panel for the type. We encapsulate everything and leave an opening for the area of the type. We laminate the type. Then we put the electrolyte, which is a potassium hexafluorophosphate. And this is how the circuit look like after encapsulation and finishing it. And then we made devices. We made the circuits, and you see here, this is an example of an inverter. Again, the gain is quite nice. The switching is very close, 0.4 volts. The resistors are balanced. And also we made a number of circuit elements. Obviously, the transition frequency is on the order of few hertz because we are using an electrolyte as a gate dielectric. We can use this type of inverter to transduce to amplify, a voltage. For example, when you move your eye you create a very small potential, which is in the order of sub-millivolts, and which is very difficult to track. But if you use the inverter, you can see the switching of the voltage in both directions. You can move the eye up and down or left and right. Okay, so with this one, I conclude. I went a little fast. I apologize, but I hope I convince you that porosity can be achieved in many different ways, with and without polystyrene. And by using a porous structure, you can get better ion penetration. The porous honeycomb structure are also elastic. If the structures are elastic, you can make, by using a pre-stretching platform, transistors which are insensitive to the current, is insensitive to the deformation. So you can use these circuits to control signal. If you want to track the signal, you want to have a transistor where the performance changes when you stretch. But if you are just use a controller, then you don't want the performance to change. And honeycomb is I believe, is one of the possible strategies to go. I also show you that the vertical OECT, where both electrodes are porous, so there is no ion penetration from the top or the bottom, the ions have to penetrate from the side, can be very efficient to promote ion, electronic, and ionic transport in OECT. And they can be very fast also, and we can make circuits based on them. And the last, we can take the advantage of the P-type organic with an N-type, P-type porous organic with an N-type dense inorganic to make electrolyte-gated circuits, again, which can be used to track physiological signal. I acknowledge all the people in the view graphs. These are some of the group member. Obviously at Northwestern work, a lot of work done with Tobin. And for the oxide also with Bedzek. Most of the work for the vertical OECT. Also Jinhua for the stretchable transistor. Xinming for all the last work on the electrolyte-gated transistor, electrical double-layer transistor was the work of Xinming, and all the other collaborators for the microstructure. And I thank you for your attention.
Okay, thanks for your great talk. And now it's time for question or discussion. Professor Wenping, please.
Okay, Antonio, thank you very much for your really, really excellent talk. You have so many excellent results recently and published so many top papers. Yeah, it's really great. Yeah, Antonio, I'd like to ask 2 questions. The first is about your honeycomb structures. Yeah, I think this structure is very interesting, and it is a kind of self-assembly structures, and how to get, for example, the most beautiful scheme structures for this kind of honeycomb structures.
Yeah, this is a very important question. Really, in order to go from a this is from a polymer organic. Also, this is from a polymer organic. These are not very beautiful structure. These are not very good. And this is a really nice honeycomb structure with holes that go through, not just crater, are really holes. And there's really 2 important aspects you need to have. First, you have to have polymer which has both hydrophobic chain here and hydrophilic chain. You need both. Also, what is most important is all these films were fabricated on glass or on silicon oxide. Instead, this film was fabricating glass or silicon oxide with a little bit of polyvinyl alcohol film on top. And then you deposit your polymer. And the PVA likes water very, very much. in a very controllable manner. So the water can condense here very, very well. And this really creates this self-assembled morphology that gives this porosity. So really you need this PVA. Makes a huge difference in going from this morphology, which is more crater, to this morphology, which are really holes that go through.
And also, it is actually shows strong substrate dependence.
Yes, yes. And in fact, in order to make the device, then when you make the film here, you dip the substrate in water, PVA dissolve, so this film, they float in water. So you can take the film and transfer them to make these devices. So here, in all the device I show, the honeycomb are not prepared directly on the OECT, but they are prepared on another film, on another substrate. It floats in water, and then we pick up the film and we transfer them. So this is the way how we can make these devices. So PVA has a two function: sacrificial layer and make good honeycomb.
Yeah. This is very important. This is very interesting, and also this structures is actually probably very useful for your OECT devices. And my second question is about your Nature paper about the OECT, and you just mentioned for the channel length between the source and the drain, you need to photolithography, because the distance is around 1 micrometers. Yeah. And have you the experience? The 1 micrometer is the best or the optimal channel length, or what range is the best channel length for this kind of device?
Yeah, you usually really need to have a very small channel length, and the reason is because the bias you apply through the gate is very, very small. It's just a very, less 1 volt or less. Okay, so if your source and drain is too far, you don't get an electric field strong enough to move. So you have to have very small channel.
Okay.
Clear. This is what is, if you make it too big, you just measure nothing.
Okay, thank you very much, Antonio. Now, Licham, because I found there is many other questions, I leave the time for others. Yeah, thank you. Yeah, thank you, Antonio.
Okay, thanks, Professor Hu. And there are some questions in the meeting room. The one is from Nadine. He asked, most of organic semiconductors have sulfur in their structure. What is the basic chemistry behind this?
The fluorine. Yeah. There is fluorine, right?
I mean, maybe you can check it in the
chat.
In the meeting.
No,
meeting
you read
room.
it. You read it very well. Yeah. Sulfur. Yeah, sorry. Yeah, sulfur. Yeah. Yes. Most of them have sulfur, and the major reason is sulfur is the soft atom. It means that the electronic clouds really likes to diffuse, and this diffusivity of the cloud helps the pi conjugation of the core of the aromatic ring, and also help the stacking when the molecules stack to have a very high electron coupling. So that's the major reason.
Okay, and another audience from Tianjin University, Yining Ma. Thanks for your excellent report. I have 2 questions, hoping to get answer. What is the energy level of materials like NBA T2 in page 6? And how to design the OTFT, and how the stability of devices, and whether the uniformity of the large area preparation can be guaranteed?
Yeah, very good question. Let me see if I can go back. It's a actually very acute question as well. I move the chat on the side. Okay, so this is a very good question. Obviously you remove carbonyl, right? So if you remove carbonyl, your LUMO energy starts going up. So you made the polymer more planar, but at the same time, you have CO are strong electron withdrawing, right? You remove them, and the energy level for this unit is on the order of -4. And if you go to this unit, you are in the order of 3.4, 3.5, roughly. So the LUMO goes up. And in fact, in order to get good N-type, you cannot, if you would make this unit with the T2, like similar to the N2200, this would be an N-type, but is not stable in air. You really need to have another electron withdrawing unit to bring back the energy down. I didn't have time to go into the details. So you really have to balance the effect, planarity, but also the energetically. In terms of uniformity, is a very important question. For these polymers, I don't know what is the uniformity over large area. I don't have experience. We never made devices like in big area. But for other molecule, I made the devices on an area which is 0.5 meter times 0.5 meter, and the uniformity is less than 6%. So it all depends how you control the coating, what type of molecule, what is the formulation, what is the environment. But OTFT can be very, very uniform if you control the conditions. I really believe that.
Okay, thank you. Another question from Yongxu Hu. Hello, Professor. I'm a student from Tianjin University. Thanks for your wonderful report. I would like to ask you a question. How stable are semiconductor materials with intramolecular lock?
Good question. So these are examples of intramolecular lock. For the oxygen is a very low mobility, and this is typical for this type of molecules. Oxygen has never been very, very good for as a furan or as an alkoxy. It's not really been very, very good typically. But if you see selenium and sulfur, their type mobility is very, very high. Those are very stable mobility. You see here, this is an example of reproducibility. The reproducibility, the standard deviation is very, very large. You see from the maximum number to the average, you have a factor of 2. And this is because the way these devices were made are by blade coating, and so the quality of the film is not optimal. So in terms of stability, the devices are stable. In terms of uniformity, this is something we haven't studied, and it is shown here. The standard deviation is very, very large, right? It's 25%.
Okay, thanks for your reply. And I have 2 questions. The first one is about the electro-gated OTFT. In our experience, generally the electric-gated OTFT have the big hysterias. Do you have the similar problem, and how to resolve it?
Yeah, it's a little bit all relative in the sense that this is a very, very important. Do I have the? Yeah, I don't. Unfortunately, I don't have. This is an example where I should remove this. But this is an OECT, right? The black was the dense film, and the red is the porous film. You see here that in this device for 3HT, when you go to the porous film, you enhance the current, but the hysteresis remains huge. The major reason is because in this film, we have a polystyrene inside a little bit. So the ion really is difficult to penetrate. But when we go to devices like this, where there is no any polystyrene and you have a honeycomb, see here the hysteresis is quite reasonable for an ionic couple device. And the honeycomb film the hysteresis is low, much lower compared to the dense film. So when you go to a film which is porous and it has a little hydrophilicity, then the hysteresis can be suppressed quite a lot. It's still not ideal. You still have some hysteresis in the subthreshold region, but it doesn't affect. You can make good devices. If you go to the vertical transistors, the hysteresis disappear. We don't see any hysteresis. They're very fast devices, incredibly fast. We still don't understand a lot of aspects. We don't understand how the ion can penetrate. You have only 100 nanometer, and they have to penetrate, 50, 100 micron. This video here, probably you haven't seen very well. And let me turn it on. This is 2 centimeter. Show the video. Boom. See? Did you see the?
Yeah, I can see the video. Yeah, it works.
At the front, you see the boom going back and forth when the voltage changes, and so we still don't understand. This is still mysterious to us why the ion can penetrate so fast. We speculate, but we still don't know.
Okay, it's interesting. Yeah. Another question is about the honeycomb structure or the porous film. Can you control the size of the density of the porous in the film? And how to control it?
Yeah, a little bit. We can control it to a certain extent. I don't have the image here, but it is in the paper. I don't know if I have in my supporting information now. We can control it by changing a little bit the concentration of the polymer, and a little bit changing the ratio. The solvent typically is a very volatile solvent. You need a very volatile solvent because you want, during spin coating, the solvent evaporate fast, so you cool the substrate. You cool the substrate, water condense, because you made the substrate cold. Solvent evaporates, it needs heat, it cools the substrate. So usually this solution, you need chloroform, methanol, very high volatility solvents. So you can change the concentration, you can use a different ratio between methanol and chloroform. We can tune the dimension. These are on the order of a micron and a half. Roughly, we can go from about 500 nanometer to about 2-3 microns, something like that. Okay. So it can be changed by concentration mostly, and changing the solvent.
Okay, thank you. And is there any questions or comments?
Yes, may I have 2 quick questions? Very impressive talk, Antonia. Thank you. Yeah, so the first question is, it's actually quite brilliant that you combined IGZO, this inorganic channel, with this OECT. So my question is, if we want to combine, both P and N type OECTs, and we know that the electrolyte is actually shared, right, by all the devices. So how to realize individual gating if we create this OECT-based circuits?
Yeah, that is a very good question. That's a very good question. I guess you need to, obviously your electrolyte has to have both ion that can penetrate in either one, right? This is what is key. It is necessary. I mean, one of the things we are doing now, all the data I show you now are using liquid electrolytes. What would be very important for circuits and real circuits is to have electrolytes which are solid. And this is something where we starting doing a little work, but it remains a little challenge. So I think you could either use solid electrolytes, which have different, which have to be patterned. So obviously it requires more work. Mm-hmm. So I think it's, either one you need a little, or having solid electrolytes where both ion can penetrate might be a little more challenging. Obviously you can have ion gels or something like that. But I think it is a very important question. I mean, I think it will require work to really make circuits which can be really individually addressed.
Right. Yeah. So another question is, I think this VOECT construction is also quite interesting, which can not only boost up the transconductance of each individual transistor, but also saves a lot of spacing. So this would be especially important when we want to fabricate like high density, high resolution VOECT arrays, right? And so what is the highest resolution that you could get currently? And do you think this could be quite promising for constructing high density EcoG array for maybe functioning as the neural interface in the future?
Yeah, that is actually we had the paper is still not out, is in press, so I cannot talk to the press and things like that. But excuse me, this was what we had a little, discussion with the reviewer, because the reviewer said, well, it's not true that you can make higher density circuit using VOECT versus the planar. But the fact is we can, and in fact, with a planar architecture, it's almost impossible to stack a P and N type exactly on the same area and make an inverter. And in this architecture, the source and drain are also the leads, are the leads contacts are also the source and drain. So definitely we can. This can it must be more dense. You can really make more dense circuits. Right. The minimum we have done, it was about I think it was about 20. So we did 20 by 20 as array. We are now using actually an e-beam lithography to make very, very small vertical circuits. As this is a work in progress, I cannot discuss it now. But we can go down to very, very small devices. And when you go smaller devices, at a certain point, see here, this is a linear plot, but it doesn't go to zero, right? I didn't say that, but if you're very careful, it doesn't go to zero. So it means the slope is not ideal. So indeed, when there is something you need to do, the ion at a certain point will be having hard time to go inside, right? When you actually go smaller channel, this deviates and it actually gets more steep. And it is there where you really can get either much faster operation.
Exactly.
Yeah. So to answer your question, we went to 20 by 20. There is no problem. When you go below that, we are using e-beam lithography to pattern the semiconductor also, to make the semiconductor extremely patterned. Here we use photolithography, and this is the semiconductor which is patterned. We can pattern the semiconductor because we have this additive. This is a photoresist. Photoresist which is blended with the semiconductor, and this allow us to pattern the semiconductor. But it's not very clean patterning. It's not ideal. To really pattern it, we use e-beam lithography, and we can get much better performing circuits.
Yeah, really, really promising. We indeed look forward to reading this work. Yeah.
Thank you.
Thank you so much.
Thanks for your professional questions. Can you introduce yourself?
Yes, Professor Li and Professor Hu. It's very nice to see you. My name is Xiaoming. I'm currently working at Tsinghua University, in Shenzhen. Yeah, Xu Xiaoming. Yeah. So Antonio, we also look forward to the opportunities maybe in the future to invite you to give a lecture or talk at Tsinghua University.
Thank you. Excuse me, I have a little cold. Thank you.
Take care. Yeah, thank you.
Okay, you can contact Anthony, in the future. And
yeah, sure.
But I don't have COVID for now. I don't know. I haven't got COVID yet. I'm sure I'm going to get it at a certain point.
Take care.
Okay, any further questions or comments? Okay.
Teacher, in the meeting room, there is some questions.
Oh, okay. Please wait a minute. Another question from Xiran Pan. Thanks for your wonderful report. I have a question. Do electric stretchable polymer have anything in common in chemical structure? Does the choice of conjugate backbone and the choice of the side chain have an impact on the mechanical properties of materials?
Yeah, I mean, this is a very important question. Usually, this is well known to a certain extent in the sense that, many of the conjugated polymer, which are the most performing, are very textured, right? Are very crystalline. And, crystallinity usually is associated with a higher modulus. So one way to try to work around that is to have either a semi-crystalline or, close to an amorphous polymer, and at the same time have a good charge transport. And these two properties, usually they contradict each other. So the best strategy that I believe it, and this has been shown by work of others, is to either being able to create fibers of a very textured area blended with an amorphous region of the same polymer, and this is where usually you get the best results. So create the fibers which are interwoven and which really, when you stretch it, you really help to get a low modulus to an elastic regime. So the chemical structure you need to think about in a way where you get either the fiber formation or in the way where you another way to do it is by changing the molecular weight. Usually you have a much higher molecular weight. You have a region which are amorphous and a region with good charge transport. That also is very it also helps. For example, if you look at this polymer, N2200 here, see if it works. Here. So here I put the molecular weight. So the crack-on set for N2200 at 47,000 kilodalton, about 3. But if you make N2200 with a 60 kilodalton, the crack-on set is almost 50%. Exactly the same polymer. And the mobility is also very similar. So there is different tricks you can do to enhance the elasticity, the plasticity. You can have most of these polymers are not elastic, are plastic. So you stretch, the morphology changes. And this is actually what it changes, why the charge transport changes when you stretch them.
Okay. Hello, Binghao Wang. Do you have some questions?
Oh, yeah, okay. Yeah. Hello, Antonio. It's very nice to meet you. Yeah, that's a very nice talk. So I'm very interested in your Nature paper about the vertical VCT. You mentioned that this type of devices has a very fast switching speed. So, but you do not mention how fast of this kind of VCT. Is this comparable to the CMOS devices?
No, I mean, not silicon CMOS, but I said it. Yeah, this is a very good question. I mean, what I meant fast. So these are these are for devices which are 30 microns times 30 microns. Okay. Excuse me. And so here we are in the microseconds, hundreds of microseconds. What I meant fast is these numbers are similar to the planar architecture, where the electrolyte is exactly in contact with the whole semiconductor. So they remains quite fast. So obviously we are not near to the silicon CMOS devices, or also many in the case of the organic TFT, but they are relatively fast. I would say they are good enough for if you want to make circuits which track physiological signal, or this type of more bioelectronics. Let's put it like sensor bioelectronics application.
Yeah, I think it's enough for the medication information. So you also mentioned that you can reduce the source drain gaps. I mean the contact area by using the EBL lithography, E-beam lithography, right?
Yeah.
So in this way, it can also enhance the speed of the devices.
Yeah. In fact, you can make either this number can go down. There's three sets of number here. So this is the sort of the is a middle range in terms of length. Okay, if you go to very, very large, then this slope starts saturating at a certain point because it's just very difficult for the ion to go in.
Okay.
If you go below this number, then the curve steeps quite a lot. And it is here where you can get a faster response. So we are now studying this area much more in more detail.
Thank you.
Hello. Thanks for your question, Binghao. And you look so fat recently. And
Chubby.
Yeah, winter is coming.
That's the final question, Anthony. Yeah. Thank Professor for your great talk. I'm recently working on OECT. I'm curious, can honeycomb structure be compatible with VOECT, making it stretchable? Will it short the channel by electrolyte in honeycomb?
Yeah, this is a very good question. It's something we haven't tried yet. The major problem is if you use the honeycomb structure. This is the final question, I guess. I don't want to. It's so late there. You use the honeycomb structure, and then you deposit gold on top. Then the gold is going to penetrate. You short the device, so it's very difficult. Because you vapor deposit gold on top of here, right? You have a gold underneath. So if you have gold on gold, then you short the device. So I think it's going to be very difficult to use the honeycomb structure in a vertical architecture, unless you find some way to fill up this gap with something. But
okay. Thanks for your reply, and thanks for your great talk and detailed answers. And we hope we can invite you visit China, visit Tianjin in the near future. Yeah.
Thank you so much.
Okay,
thank you. Thank you, everyone. Thank you, Wenping.
Yes. Antonio, just make your schedule carefully, and when you decide the period to visit China, please make sure to tell me. Okay.
I will.
To stay in Beijing and Tianjin for some time.
Thank you so much. Thank you so much.
Great. And I hope to meet you soon in China. Well, yeah.
Thank you.
The COVID-19, I'm sure. Yeah, after 1 week will be almost the peaks will be passed. Yeah, in Beijing and Tianjin. Yeah, and now especially in Beijing, it is almost recovered daily life as originally. Yeah, it's okay now. Yeah, and Tianjin probably after 1 more week. Yeah.
Everybody went through the same thing. Everyone. It happens in Chicago, in Italy. Everyone. So
yeah, that means the whole world will be returned to normal life. Yeah, that it will be great for our academic community.
Yeah, I understand.
Okay, see you. Yeah,
Okay.
and hope to see you soon.
Okay.
Yeah.
Okay, bye-bye. Happy New Year.
Bye.
Chinese New Year.
And
Bye-bye.
every friend, and bye-bye.
Okay, thank you. Yeah. Bye.
Enjoy your life. Okay, bye.